I have to get something from the printer.
Yeah.
And then you forgot to say
That was so heartbreaking. That's like my favorite part of this class.
So, this is going to be an embarrassing beginning of the video. Okay, so we're going to talk about probability. And a couple of definitions, which of course are things you already know.
So this is a set of outcomes or events. That's what A is.
And the probability of A is, of course, the sum of the probability sub J of each of the ways in which an outcome or event can occur. So, for instance, if you have dice, then the probability of getting 1 followed by 1 is 1/6 squared, or 1/36. The probability of getting 3 is the probability of getting 1 and then 2 plus the probability of getting 2 and then 1. In each case, this is 1/36 plus 1/36, so this is 1/18. So let's just warm up to familiarize you, to wake up the neurons that are relevant to this outcome. Okay, now, suppose you have A and B are two sets of possible outcomes. This is the union and A intersection B. So this is the set of outcomes that are in either A or B or both. This is the set of outcomes that are in both A and B. And what we have then is that the probability of orb is the probability of A plus the probability of B minus, I guess, what's called the joint probability, P of the intersection. So this is called intersection, this is called union. In LaTeX lingo, this is \cup, and this is \cap. If you're sitting in front of a computer, you can just Google all these things. So the joint probability is P of A comma B, and I think a better way of writing that is P of A and B. That means the probability of something, of an outcome occurring that's both in the set A and in the set B is that. And if the probability of the joint outcome is just P of A times P of B, then we say that the outcomes are statistically independent. Then outcomes A and B are statistically independent. So, in other words, the probability of getting both A and B is probability of A times the probability of B. Whereas if B implied A, if B were a subset of A, then the product of these two would be smaller than necessary. So this would be too small, this would be less than that, I would think. Anyway, so something that we think about a lot, we often run into, is the probability of A given B. So this is A given B. And what we can say is that the probability of A and B is the probability of A given B times the probability of B. But on the other hand, it's also the probability of B given A times the probability of A. Okay, so let's think about these two. Probability of getting both A and B, of an outcome being in both sets, is the probability of B. Now, once you have B, you multiply that by the probability of getting A given that you've got B. Or equivalently, it's the probability of getting A, then times the probability of getting B if you've got A. Okay? All right. So, this, in fact, is, let me just, I've decided to rewrite this just as tad. Oh, this, in fact, gives us Bayes' theorem. And
Bayes' theorem. Bayes, by the way, lived quite a while ago, 1702 to 1761. And what we do is we just set these two things equal. And so what we have is the probability of A given B from this equation is the probability of B given A times the probability of A divided by the probability of B. So in other words, we just set this equal to this and divide both sides by P of B. So that's Bayes' theorem. But there's just interchanging A and B, we get another version of Bayes' theorem, probability of B given A. Whoops. So probability of B given A, we divide this equality both sides by P of A, and then what we get is P of A given B, P of B divided by P of A. So those are some results, and they seem, just obvious. How could they be wrong? And yet, when we start applying them in particular cases, all of a sudden, we get very surprising results, which are correct, actually, but they're still surprising results.
Could you give an example of one of the applications for that?
Give an example of what?
Of one of the applications
That are going to be surprising?
for the Bayesian.
Oh, yeah, we'll get to that in a minute. Let's first look at this case. Where was it now? I'm confused as to where I wrote this down. Okay, so what we can always say is the probability of B is the probability of B given A times the probability of, wait a second, I'm not. I wrote that down here, but I'm not sure, is that really true? I mean, no, I don't think this is actually true, so let's skip this. I don't think, because after all, you could have B without having A, right? So this is something spurious there. What instead I want to do is take this relation for the case in which, suppose A is a union, I guess we say K equals 1 to N, whatever, of A sub, let's see, what am I saying? A sub J. So, and that AI intersection AK is the null set. Then what we can say is that the probability of a particular A given B is the probability of B given AK times the probability of AK. But now the probability of B, well, I am going to use a relation like the one I wrote down. This is going to be a sum on J equals 1 to N, the probability of B given AJ times the probability of AJ. So this is in a case in which B, in other words, I'm assuming here that the probability of B is the sum probability of B given AJ, probability of AJ. So this is in that particular case. In other words, B can only occur if one of the AJs occurs, and also the AJs are mutually exclusive. Okay. These P of AJs are sometimes called a priori probabilities. And sometimes they're just called priors. And of course, that should be confusing. So let me apply this formula then to what's called the low base rate problem. So suppose you have an incidence of a disease in other words, this is a rare disease. And suppose, on the other hand, that we have a test for the disease that's really good. That is to say, it's really sensitive. And so that the probability of a positive result of the test, given that someone has the disease, is 0.99. So that's pretty effective. It's 99. It works 99% of the time. And suppose it's also highly selective. So this is sensitive. And it's also selective in that the probability of a negative result, given that, a positive result, given that the person doesn't have the disease, is 0.005. So this is said to be selective. So in other words, somebody comes into the clinic, has a disease, the test is going to give a positive result 99% of the time. If someone comes in, doesn't have the disease, it's going to give a positive result only 5 times in 1,000. So this is a pretty good test. Now, what's the probability that a random person tests positive? Well, it's going to be the probability that the person is diseased, and that times the probability of a positive result given disease, plus the probability of a positive result given not having the disease, times the probability of not having the disease. So this is where, in other words, I'm applying this result here because in this case the AJs are diseased or not diseased, which are non-overlapping, and the way to get a positive test is only if you either have the disease or don't. We don't consider a case where you have a mild case or you have some other disease or whatever. Okay, so I've got to rewrite this.
I have a question.
Yeah. By the way, I have no candy. I ran out.
Oh, don't worry.
Sorry about that.
I wonder why. But
I don't know what you're looking at. I don't eat the candy ever.
You're awesome here.
Yeah.
Why is that a plus and not a minus? Because me rationalizing it in my
the
head.
probability of getting a positive result are 2 ways.
Oh, positive result.
For a random guy staggering into the clinic. Okay. All right. So that's how it works. On the other hand, Bayes' theorem is going to give us a formula for this, for some of these things. Namely, the probability of the person being diseased given a positive result. Well, what is it? It's the probability of a positive result given disease times the probability of disease divided by the probability of a positive result. So that's just the Bayes' theorem in this form or that form. And we can compute this. This is 0.99. This is 0.001 because it's a rare disease. And we divide by this thing here, which I forgot to calculate, namely, wait a minute, what am I doing here? Yeah, I forgot to calculate this, so let's calculate this. This thing is plus D is 0.99. Probability of disease is very small, that's 0.001. Plus probability of positive given not diseased, 0.005, times probability of not diseased, which is 0.999. And altogether, this is 0.005993. Okay. So now what we do is we stick this number, which is probability of a positive result from a random person, and we stick that there, and we have 0.005993, and what we get is 0.165. So this is telling us then that the probability that the person is diseased or is a carrier, given a positive result, is only 16.5%. So in other words, even with a sensitive selective test, if the disease is rare, the reliability of the test is really quite awful, and the probability of N of not having disease given a positive result, which is to say a false positive, is of course 1 minus P of D plus, which is then 0.835. So in other words, what we've got is a false positive rate of nearly 84%, and and we're telling 16% of the people tested that they have the disease when they don't. Right. I'm sorry, that they. No, I got it wrong. We're telling of the people who have a positive retest, the number of diseased are only 16%. And so those two things correlate. So that's why with an excellent test, screening for rare diseases is problematic. And of course, screening costs money also. And so it's a medical problem that's well known in the community. Unfortunately, people nonetheless ignore these sorts of results. And for example, one test that is not a good test, I mean, this is a terrific test, okay? It's sensitive and selective. Polygraphs, on the other hand, are lousy tests. And disloyalty in the FBI is a rare thing. And so using a polygraph, which is a bad test, to look for a rare occurrence like disloyalty in some organization like FBI, CIA, whatever, is really a crazy thing to do, and yet they do it. Of course, they didn't take this course. By the way, Bayes was actually a minister of some sort. All right, the next one, if you thought this was a little surprising, the next one is a real head turner. It's the 3-door problem. You've seen it? It's weird.
It's
Yes.
weird.
Yeah, all right, I completely agree. I'm just getting another piece of chalk, so don't turn the thing around. Okay, so here's the 3-door problem. We've got 3 basically rooms. One of them has a prize, and there are 3 doors, obviously. And a contestant has said, okay, there's a prize behind one of them, in one of the rooms, the other 2, nothing. And so the contestant is asked to guess, choose a where do you think the prize is? And so the contestant may say, I think it's there. And then what the guy does is he says, okay, here, let me get the eraser. He opens the door of one of the rooms that hasn't been chosen and does not lead to the prize. Okay. So he opens, say, this one. And so now the contestant has said, do you want to change and switch to maybe this one instead of that one? Okay. And of course, you know, if you were the contestant and hadn't worked through this problem, you wouldn't know what to do, or at least I would. And so let's work it out. Okay. So first of all, the probability of winning, given that you switch and pick the wrong door, well, that's going to be 1. Okay. In other words, you pick at the first stage, you picked the wrong door, and then you switched, and then the probability of winning would be 1, because in this case, the prize would be here. You pick this one, you switch, and then the probability of winning is 1. The probability of winning, given that you switched, but you picked the right door to start with. So in other words, you picked this one, and then you switched. Well, then you're over here, and so you've got the wrong one, so that's 0. I'll be putting these notes on the class webpage. Okay. Now, something very simple is probability of picking the wrong door is 2/3, because there are 2 that don't have the prize and only 1 that does. Okay, and of course, probability of picking the right door is of course 1/3. All right. So, what is the probability of winning if you switch? Well, this is probability of winning given that you switch and you pick the wrong door times the probability of picking the wrong door plus probability of winning given that you switch. In fact, I should use intersection here. Right door times probability of right door. Okay, so what are these? Well, probability of winning, given that you picked the wrong door and switched, that's 1. So this is probability of wrong door. And then this is probability of winning, given that you switched and you picked the right door, that's 0. So this is just this, and that is 2/3. Okay. What about the probability of winning, given that you stayed put? SP. Well, that's probability of winning, given that you stayed put and picked the right door, times probability of right door, plus probability of winning, given stay put and wrong door, times probability of wrong door. Okay, so what's this? Probability of winning, given that you picked the right door and stayed put, that's 1, times probability of right door, that's just 1/3. Now over here, we've got probability of winning, given that you picked the right door, the wrong door and stayed put, that's 0. Pick the wrong door, stayed put, probability of winning 0. So, remarkably enough, the probability of winning, if you switched, is 2/3. Probability of winning, if you stayed put, is 1/3. So, remarkably enough, that's how it works. And it's pretty amazing. Now, we had Bayes' theorem over there, and let's look at that. All right, here, let's swing the thing around the camera, because I'm going to rewrite this. Suppose we let a sub k go just to x. In other words, the probability of something having a real value x. Then this would be probability of x given b is probability of b given x times probability of x divided by, and now we would have an integral of probability of b given x times the probability of x dx. Okay, so once again, these x's, of course, are different real numbers, so the intersection is 0. And we're assuming that b can only occur if x has some value, and then there's a certain probability of b given that particular value. Okay. So I'm going to apply this now to polling, and thank you. Now, before doing that, though, let me quickly jump to the binomial distribution. Say a few words about that, and then jump back to the polling. So, suppose we have probability of success is p on each try. This is probability success on a try. So if you have in n tries, the mean number of successes will be n times the probability of each one. And we're also going to just set q as 1 minus p is probability failure on a try. Okay, now, so what's the probability of a particular sequence of probability of a particular sequence of n successes I'm just checking that I spelled successes. N successes in capital N tries. Okay, well, what will that be? Well, it'll be p to the n q, or 1 minus p, to the big N minus n. So that's the probability of a particular sequence of successes, say a run of little n successes followed by big N minus little n failures. That's the probability of that. On the other hand, there are lots of sequences of little n successes in big N trials, and the number of them, well, what is the total number of sequences? The total number of sequences is n factorial. On the other hand, we're not distinguishing among the successes, so we divide by little n factorial, and we're not distinguishing among the failures, so we divide by that. So that is the probability n successes in big N tries. Okay, so it's the probability of a particular sequence times the number of sequences that have that number of successes. And this is often written as binomial coefficient p to the n, 1 minus p to the n minus n. And now, if you remember the formula, x plus y to the n, that's the sum n x to the n, y to the n minus n. Okay? N equals 0 to capital N. That's the binomial expansion. You can verify it for n equal to 0 or 1 or 2 or 3, and then you can Google it for the rest of them. Well, I shouldn't say that, but anyway. Now, consequently, what's the sum of these probabilities? So the sum of the binomial probability of n successes, if the probability is p, and that's the number of trials, well, that's the sum, n equals 0 to infinity, of n, p to the n, and now this is 1 minus p to the n minus n. Well, this is just p plus 1 minus p to the n, which is 1 to the n, which is 1. So the sum of the probabilities is unity, which is what one expects, namely of a probability distribution that anytime you do capital N trials with probability p, you're going to get some number of successes, so the sum of all the probabilities has to be 1. All right, so let's suppose, now we'll go to the polling. Is there a question or something? Let's suppose we go to the polling example. And suppose y is the probability that a person will vote, a random person, her son, will vote for, and I picked Nancy Pelosi. Of course, this is somebody in San Francisco, where I think that's her district. Okay, so now let me switch back to the Bayesian example. Okay. So if y is that probability, because we don't know what that is, then the probability that 3 out of 4 people, given that the probability is y, what is that? Well, that is going to be 4, 3, p cubed, that's y cubed, sorry, 1 minus y, and that is 4 factorial over 3 factorial, 1 factorial, and so that's 4 times y cubed times 1 minus y. All right. We're just warming up here. Now, what I should have said before I computed this thing is that suppose we did a very cheap poll. Instead of asking 1,000 people in San Francisco whether they would vote for Nancy Pelosi or not, we just asked 4 people. And 3 of them said they would. Okay. So that's a good sign. But what can we infer from it? And, well, what we can infer from it is, maybe I should go to the whiteboard because I'm out of space. Okay, so what we're looking for at the moment is, it's not that, we made a mistake. The probability that, and I hate to say this because it's the word probability, it's occurred twice, but this is the probability that if 3 of the 4 people said they would vote for her, what's the probability that a random person will vote for her? That's y. Okay. Using this formula over here, we see we replace x by y, we replace b by 3, and what we get is that this is probability of 3 given y, probability of y, but then we divide by an integral over all possible values of y, and probabilities just run from 0 to 1. P of 3 given y prime, probability of y prime dy prime. Okay, now, I just see that I'm not, oh, yes, okay. Now, we don't, of course, know what the probability of y is. If we knew that, we wouldn't have to do the poll. So instead, what we're going to do is we're going to assume maximum ignorance. And in other words, we'll assume that p of y is 1, so the integral of p of y dy from 0 to 1 is just 1, which says that probability of y must be something. The probability of y being whatever, being between 0 and 1, which it has to be, is 1. Okay. So now this thing simplifies to probability of 3 given y, p of y is 1, integral 0 to 1, p of 3 given y prime, p of y prime is 1, dy prime. Okay. But p of 3 given y, we know p of 3 given y prime then is 4 y prime cubed 1 minus y prime. Yes.
So what is the difference between y and y prime?
Oh, y is, actually I'm getting confused now because of all these probabilities, but y is the probability that a random person will vote for Nancy Pelosi. And we don't know what it is, so we integrate over it, but it's got to be between 0 and 1. But we computed what the probability of 3 out of 4 randomly chosen people would vote would be. The probability that 3 randomly chosen people would vote for Nancy Pelosi, 3 out of 4, given that the probability is y or y prime, it's that number over there. And so for y prime, it's this.
Okay. Yeah.
So what we've got then is p of 3 given y, well that's the thing we wrote down there. That's 4y cubed, 1 minus y. And then in the denominator, we've got integral 0 to 1, 4y prime cubed, 1 minus y prime dy prime. Well, this of course is just a number, and we could compute it. Shall I do the integral exactly with my fingers, or shall I just tell you what the answer
What's
is?
the answer?
Huh?
You can tell us the
Yeah,
answer.
just go with that.
Just write down the answer?
Yeah.
Because it might be wrong.
Uh-oh.
Actually, why don't I do the integral?
What's the probability?
0 to 1, 4y prime cubed minus 4y prime to the 4th. This is what the integral is, right? Right?
Yeah. That makes sense.
So, this thing is 4 y prime to the 4th over 4 minus 4 y prime to the 5th over 5, right? But now setting y prime equal to 1 just means we get rid of it. Well, all right, here, 1, 0. Okay. And so this is 1 minus 4/5, which is 1/5. So this is 1/5, so this is 20y cubed, 1 minus y, which is what's in my notes here. Okay, so now what do we know? Now we know p of y given 3. And so what's the chance that she'll win the election? Well, if y is greater than a half, she'll win. Because y is the probability that a random voter will vote for her. So now what we do is we integrate from a half to 1 p of y given 3 dy. And so this is the integral from 1/2 to 1 of that thing, 20 y cubed 1 minus y dy. And now, I guess I can do that one. It's 20 y to the 4th over 4, so that's just 20 over 4, minus 20 over 5, and so that is 20 times a quarter minus a fifth. And that is 20 over 20 times 1. Oh, God, that can't be right. I screwed up. It's supposed to be 13 over 16. What did I do wrong? Win, but this, somehow I got 13 over 16. Oh, it's not 0 to 1, it's 1/2 to 1. So let's bring in the eraser and do it right. So it is really 20 over 4 y to the 4th minus y to the 20 y to the 5th over 5, evaluated between 1 and 1/2, not between 0 and 1. So evaluating it at 1, we get 1. And now we subtract the value of this at 1/2. And I don't know what that is, but it's 20 times a quarter times a half to the 4th is 1 over 16, isn't it? Minus a 5th, 1 over 32. And all right, let me just 1 minus 20 over 32 times well, let me just tell you what the answer is. It's 13 over 16. So what actually do we learn here? The naive estimate, if you just asked 4 random, you did the cheap poll, you asked 4 people, 3 say they're going to vote for her, then your estimate for Y naively is 3/4. 13/16 is a little better because 3/4 is 12 over 16. So in other words, applying Bayes' theorem to the analysis, we wind up with a more accurate projection.
Can we do the probability for how many were gonna vote for Trump?
I'm sorry, start again? What?
I said, can we do the probability for how many are gonna vote for Trump now?
Well, we could. All right, how many, here, 4 of you, how many are gonna vote for Trump? In 2020.
What does that tell
Yeah, what's the probability now?
Is that 0?
Yeah.
Okay, so the probability we estimate then is that his chance of getting elected is 0, I think.
See, but I feel like that was the probability before.
You mean you thought that was the probability back in the middle of 2016?
Yeah. So
Well,
what happened?
I mean, everybody, all the media said that was the case, but I noticed that
They forgot to count the probability.
if I listened to a Trump speech, he was fun to listen to. I listened to a Hillary speech, he wasn't fun to listen to. Now, I voted for her, my wife voted for her, we have 3 sons, they all voted for Hillary. They have 3 wives, they all voted for Hillary. So we had 8 votes for Hillary, but she still lost. But she won the popular vote, of course. The trouble is the country is gerrymandered by the Electoral College.
I think in South Carolina, the gerrymandering is so awful it can't be considered a democracy.
Yeah, well, it's not just in
Yes.
South Carolina. There are many states. Both parties are actually guilty of it, but
Well,
the Republicans these days are more guilty because they are actually smart. And
damn it.
they did two smart things. I could be going on about this. But they did two smart things. First, they really emphasized local elections and got control of state legislatures. The second thing they did was they hired good statisticians to help them gerrymander and use computers and so forth, and you use modern technology to gerrymander. So once they had, and they took huge advantage of the 2010 census. So 2010 census, control of the state houses, using computers and good statisticians, and they nailed it. And that meant that in 2012, they won the House of Representatives and the Senate, and 2014 they probably increased their voting, I don't remember, and then in 2016 they won the president's. They had gerrymandering. Well, because the gerrymandering doesn't apply to the president. It just, apart from the effect due to the Electoral College. So, frankly, I blame the Democrats and Hillary in particular for the message they had. It was targeted to very specific, tiny groups of people, and you had 100 million Americans who weren't doing so well. And she either ignored them or called them a basket of deplorables. And that's no way to win an election. And in fact, it's not even a moral way to. Well, I guess she wasn't considering that 100 million were deplorable, but I don't know. She never made that clear as the problem. And so she lost to Donald Trump and his running mate, Vladimir Putin.
Well,
And I just wonder to what extent Putin was behind the Brexit vote in Italy and yesterday's crazy vote in, the Brexit vote in England about 18 months ago, and a 5-star victory in Italy yesterday.
He's just put Putin his 2 cents everywhere.
The people who won in Italy were populists.
Oh, okay.
Now, it could have been worse. It could have been crooks.
It was right there.
Berlusconi. But, all right, look, we're not supposed to be talking about politics. We're talking about mathematics.
Well,
But it's not
yeah,
What?
yeah, it's got
It's
something
probably
to do with
it's
it.
close. Still understand how
Okay, let me see where we are now. All right, let me make a couple of definitions then.
it's like 20 people that voted for Hillary.
Definitions, so definitions are painless. You can sort of almost turn your brain off and just, because you don't have to, really, it's just a question of memorizing or becoming familiar with these things. Okay, so in some cases, the outcomes are discrete like that and denumerable, in which case the sum of them has to be equal to 1. There's something called E of x, and this is basically, this should be called the mean value of x, and it sometimes is written like this. In fact, in physics departments it's often written like this. It's also written as mu for mean value. It's sometimes written as x bar. And of course, what it is the sum of xj, pj. Okay. And unfortunately, because the people who taught Americans quantum mechanics had German as a native language, and they call this the expectation value of x. That's kind of an abusive language. It should be called the mean value. Anyway, there's something called the Lth moment, and of course this is just xj to the L, pj. And then there's something called the Lth central, and this is called mu sub L. Then there's something called the expected value of the Lth central moment, and this is called nu sub L, and this of course is sum xj minus mu to the L pj. Okay, so those are some of the basic definitions, and if you have continuous variables, then you have an integral p of x dx is equal to 1. That's the equivalent of this. The expected value or the mean value of x is an integral x p of x dx, and similarly e of x to the L is an integral x to the L p of x dx. What I'm leaving indefinite the range because it depends on what range, what the range of variables of x is, and there's also e of x minus mu to the L, and this is an integral x minus mu to the L p of x dx. Okay. Now, one thing that's really important in probability, apart from the mean, these various means, is the variance v of x, and it's just the second central mean, and in other words, it's an integral of x minus mean value of x squared p of x dx. And it always turns out that this is equal to the integral of x squared p dx minus 2 integral of x p of x dx minus plus x squared. Well, times the integral, but the integral is 1. Okay. Now, the integral of x p of x dx is just x again, mean value of x. So this is equal to the mean value of x squared minus 2 mean value of x squared plus mean value of x squared. And so this is mean value of x squared minus the mean value of x squared. So that's what the variance always is. And this is also always the second central moment. And in physics departments, we're always talking about standard deviations. The standard deviation sigma is just the square root of the variance, which is square root of nu 2, or square root of x squared minus x squared. So that's the standard deviation. Sometimes it's called the standard error. It's the spread, basically. Now, let's skip ahead. By the way, in mathematical circles, there's a slightly different notation. We talk about P of X because we're thinking in quantum mechanics you have, for example, P of X is the wave function, absolute value of the wave function squared. We also have the Maxwell-Boltzmann distribution and so forth, and those are probability distributions. For example, P of a certain velocity will, for particles of mass m, apart from a constant, it's e to the minus m over 2v squared divided by kt, and then some factor here. And this, of course, is energy divided by kt, k being Boltzmann's constant. And so we talk about distributions in physics like that. What mathematicians often do, and so I need to warn you about this, is that mathematicians, so let me just use this white space here, they will talk about a cumulative probability distribution, which they'll often write as capital F of X. This is the probability of an outcome between minus infinity and X, and this is what we might write as minus infinity up to X, P of X prime, dx prime. And they often use little f for the probability distribution, and so this would be in math circles, it'll be little f of x prime dx prime. So that's just to connect with some of the math lingo. Okay, so let's get back to the not to the Boltzmann, but to this binomial probability distribution. And in fact, let me emphasize something about probability distributions. You hear was the Poisson distribution, the Maxwell-Boltzmann distribution, and so forth, the binomial distribution. Well, the real distribution is the binomial distribution. The Poisson distribution is Poisson's approximation to the binomial distribution, and the Maxwell distribution is another approximation to the binomial distribution. So in a perfect world, we'd all just use, all we'd ever use would be the binomial distribution. But you see, what's the problem with the binomial distribution is that it has these factorials. Okay. Now, if we're talking about a cheat poll, the Nancy Pelosi cheat poll, where we only ask 4 random people how they're going to vote, I'm not even asking them if they're going to vote, which they probably aren't. Where am I? Yeah, if it's just 4, we can handle the numbers. Although, even there, I had to just tell you the answer was 13 over 16. At least I hope that's right. When we're dealing with real situations, n might be 20, it might be 100, it might be in physical situations, in statistical mechanics, it could be Avogadro's number. Then you have something like capital N is 10 to the 23rd times 6, even worse. And then you have 6 times 10 to the 23rd, factorial. Okay. Well, it turns out that if you try to do these things on the computer, you very, very quickly get things like NaN as your output, not a number. So, in other words, the problem with the binomial distribution it's the true distribution, but it has these damn factorials which are absolutely crazily big numbers. And so there is a way of coping with them. I don't know, maybe I'll just switch, turn the thing around and erase some of the back stuff here. So, what we have is so let me just give you the computer science aspect and then try to say something else. Well, no, before I do that, I'm just going to give you a graph. Okay. This is the probability, the Boltzmann probability, little n, p, big N, okay, for what? For various cases. And this is n going from 0 to 250. And here we're going from 0 to 0.09. Now, the first case is, all right, and what's p? Little p is 1/5, or 0.2. All right. Suppose we do 125 tries. If it's 125 tries, then the thing looks like this. On the other hand, if we do 250 tries, then, and by the way, the mean here is 125 over 5, which would be 25. So the mean here is 25. If we do 250 tries, then the thing is going to be a mean of 50, and it's going to be somewhat broader. It's going to look a little bit like that. If you do 500 tries, so this is 125, 250. If you do 500 tries, the 1/5 times 500 is 100, and so the mean is here, and it's somewhat broader. And then if you do 1,000 tries, the mean is going to be 200, and it's going to be yet broader. So it sort of look like that. So what happens? The maximum probability decreases, the variance or the spread of the probability distribution spreads out, and in fact, let me just check that. These are computer graphs that I generated, in fact, in a well-known book. This was stated incorrectly, and so that's why I did the thing. What is the variance? The variance for this is P1 minus P times capital N. Okay, so if you keep P fixed at 1/5 and you increase N, the variance increases linearly with N, and so you see that's what actually is happening. What does decrease, of course, is the standard deviation. Well, let's just write it as sigma divided by the variance. So in other words, the sigma is sort of the uncertainty.
I just have to get out of this chair somehow.
Yes. Okay. So this, of course, in fact, is square root of 1 minus p over np. So this does decrease, but that's just because sigma is the square root of v. V is increasing, so square root of v is increasing more slowly. Okay, so we're basically out of time. If there are any questions despite the lack of a sugar fix.
I do have a question. So over there, when we're finding P3Y, you just did the first. It's supposed to be.
All right, let me go over there,
Okay.
or let me listen to you, and then I'll go over there.
Okay, so it's supposed to be sigma n over mp to the n, all that.
Sigma, where's Sigma over there?
You put a sigma notation.
Oh, yes,
But
that's
you,
the sum.
yeah, the sum, yeah,
So this is the thing this is the sum over all possible outcomes.
right. But you only did it for 4 and 3. You didn't follow through to.
Only did it for what?
I thought, or maybe I'm just being a dunce, but do you not need to do multiple iterations of it?
It's so the
The
summation
each
is the
probability
probability for
is
each different act.
N should
So you're
be
saying
little
for
n,
each
p to the
different
n,
n.
1 minus p to the that.
Okay,
But this is the expansion of p plus 1 minus p to the n.
okay,
That's the expansion of 1 to the n, which is just 1.
okay,
So the difference is the bottom one is the probability for one case,
Okay.
and the top one is
for all
the summation
cases.
for all the different cases.
Okay.
The probability is going to be one.
Okay,
Oh, that makes sense.
Anyway, I will try to clean up the notes a little bit and put them on the web page. And what I need more than anything, what would help me a lot would be if you find a mistake, tell me about it. I'll email it or in class. And secondly, if you think a certain sentence I wrote is clumsy and you can prove it, send me an improved version. Or if you say that there's something I should explain more clearly, say that too. Okay, I think we can turn it off if there are no further questions.